Welcome to Physical Chemistry 1 Laboratory. I am Dr. Min Soo Lim, and I will show you how to carry out the lab in the experimental and theoretical aspects. You will do a 2-week-long experiment titled Spectroscopic Determination of KEQ, delta G naught, delta H naught, and delta S naught. I want you to follow my instruction thoroughly, slide by slide. After you complete this online pre-lab lecture, you should take an online quiz that is posted on D2L. You may watch this video as many times as you need, but you have only one chance to take the quiz. In this lab, you will use Le Châtlier's principle and demonstrate how temperature change affects the formation of pyridine iodine complex, which leads to the change of equilibrium constant. You will determine two equilibrium constants spectroscopically for the complex formation, one at 20 Celsius and another one at 40 Celsius, utilizing Châtlier equation. The two equilibrium constants will be used to determine two delta G naught values, one delta H naught value, and two delta S naught values. Check how the equilibrium constant changes as temperature changes, because it indicates whether the reaction is exothermic or endothermic. Make sure that the two delta G naught values and the sign of delta H naught support your determination. Finally, you will determine two delta S naught values. Report whether the level of randomness of the system remains the same or not as temperature changes by observing the two delta S naught values. Le Châtlier's principle states if a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. Here is a generic equilibrium reaction. Reactants A and B react by a mole ratio of m to n and produce k moles of product P. The equilibrium constant can be expressed like this. Take note that the stoichiometric coefficients m, n, and k in the chemical equation act as the exponents in the equilibrium constant expression. Take note that the value of the equilibrium constant at constant temperature does not depend on pressure and the concentrations of reactants and products. Don't forget that the reaction may shift its equilibrium position to the left or right, but it is intended to maintain KEQ value constant. However, the equilibrium constant is no longer a constant when the temperature changes because the value of KEQ depends on temperature. In this lab, we will determine the thermodynamic nature of the formation of pyridine iodine complex. Pyridine is denoted by Py, and pyridine iodine complex is denoted by capital C. The double arrow implies that the reaction is an equilibrium reaction. The equilibrium constant expression of the reaction can be written like this. Now, the question is the reaction exothermic or endothermic? Suppose that the reaction is exothermic. Then the reaction would release heat as the reaction proceeds forward. It will increase the temperature of the solution or the reaction mixture. If additional heat is added externally to the reaction mixture, what would happen to the position of equilibrium? This would bring the temperature of the solution higher than expected because of the surplus heat. According to the Le Châtlier's principle, the reaction would proceed in the reverse direction until a new equilibrium is achieved. This would not only consume the surplus heat, but it would also consume the product C and produce back the reactants iodine and pyridine. it would decrease the concentration of the pyridine-iodine complex and increase the concentrations of iodine and pyridine. Consequently, the equilibrium constant decreases when additional heat is added to the reaction mixture. In other words, in an exothermic reaction, the equilibrium constant at high temperature is always less than the equilibrium constant at low temperature. The opposite is true for an endothermic reaction. It further implies that we may easily determine if an equilibrium reaction is exothermic or endothermic simply by observing how the KEQ value changes when the reaction mixture is heated or cooled. We can convert the equilibrium constant to standard delta G, or simply delta G naught, by using the following equation. Delta G naught equals negative RT times log KEQ. The equation can be modified with respect to KEQ, which is KEQ equals e to the negative delta G naught over RT. Take note of the negative sign in front of the log. As KEQ decreases, delta G naught increases. Suppose that a reaction is exothermic. Since the KEQ value at high temperature is less than the KEQ value at low temperature, the delta G naught at high temperature is greater than the delta G naught at low temperature. Delta G naught can be converted to delta H naught, utilizing the Van 't Hoff equation. Take note that delta H naught will be assumed constant at the temperature range between T low and T high. You may plug the two KEQ values and two temperatures in the equation and solve the equation for delta H naught. In an exothermic reaction, delta H naught should be negative. In summary, the KEQ value at high temperature should be less than the KEQ value at low temperature. As a result of it, the delta G naught at high temperature should be greater than the delta G naught at low temperature, and delta H naught should be negative. The opposite is true for an endothermic reaction. Remember that the two KEQ values, two delta G naught values, and one delta H naught value should be consistent with the thermodynamic nature of the reaction, whether it is exothermic or endothermic. The last step is to determine two delta S naught values at two temperatures, utilizing the equation delta G naught equals delta H naught minus T times delta S naught. Observe whether delta S naught increases or decreases as temperature changes, and include your interpretation of the trend on the change of delta S naught in your report. The first step in this lab is to prepare two stock solutions. The first stock solution is a 25 milliliter 0.050 molar pyridine solution in cyclohexane. All information that you need for the solution prep can be found in the label of the chemical bottle. Now, I will show you how to determine the required volume of pyridine to prepare a 25 milliliter 0.050 molar solution. Be aware that pyridine is a colorless liquid with a disagreeable odor. Since pyridine is 99.8% pure, put down 0.998. The volume of pyridine to be transferred is set to X milliliters. The density of pyridine can be used to convert the volume to gram mass. The molar mass of pyridine converts the gram mass to moles. Divide the moles by the volume of solution, which is 25.00 milliliters or 0.02500 liters. This should be equal to 0.050 molar. Units, milliliters, and grams are cancelled, and moles over liter remains. which is equivalent to molar. Solve the equation for X, and it is 0.101 milliliters. The little bar on top of 0 represents the last significant number. Now, obtain a bottle of pyridine and transfer a little over 0.101 milliliters of pyridine to a clean and dry 50 milliliter beaker. Do not take the required volume of pyridine directly from the bottle. It may contaminate the whole bottle if you do so. Save chemicals as much as possible. Use a 1 milliliter graduated pipette and transfer 0.101 milliliters of pyridine to a 25 milliliter volumetric flask. Make sure that all glassware is clean and dry prior to using it. Fill the volumetric flask with the solvent cyclohexane to the 25 milliliter mark. Don't forget to follow the stepwise mixing procedure. Fill the flask approximately 2/3 full and mix. Carefully fill the flask to the 25 milliliter mark. And this is a 25.00 milliliter 0.050 molar pyridine stock solution. The second stock solution is a 25 milliliter 0.0120 molar iodine solution in cyclohexane. Check the label on the bottle of solid iodine for the information that you may need for solution prep. Since iodine is 99.8% pure, put down 0.998. The gram mass of iodine to be transferred is set to Y grams. The molar mass of iodine converts the gram mass to moles. Divide the moles by the volume of solution, which is 0.02500 liters. This should be equal to 0.0120 molar. Unit gram is cancelled and moles over liter remains, which is equivalent to molar. Solve the equation for Y, and it is 0.0763 grams. Weigh 0.0763 grams iodine and transfer it to a 25 milliliter volumetric flask. Fill the volumetric flask with cyclohexane to the 25 milliliter mark. Don't forget to follow the stepwise mixing procedure. Fill the flask approximately 2/3 full and mix. Carefully fill the flask to the 25 milliliter mark. And this is a 25.00 milliliter 0.0120 molar iodine stock solution. 6 sample solutions should be prepared by mixing the required volumes of 2 stock solutions according to this table. Use 2 graduated pipettes and transfer the required volumes of the stock solutions to a 25 milliliter volumetric flask. Do not mix up the pipettes. One pipette should be used for transferring pyridine stock solution, and the other one should be used for transferring iodine stock solution. After transferring both stock solutions, fill the remaining space of the flask with cyclohexane to the 25 milliliter mark. Follow the stepwise mixing procedure. 6 sample solutions, A, B, C, D, E, and F, should be prepared using the same method. Now, 6 sample solutions are ready to use. Suppose that the lower temperature is 20 Celsius. Take note that the lower temperature can be lower or higher than 20 Celsius in normal laboratory settings. But make sure that the temperature difference between low and high temperatures is at least 20 Celsius for this experiment. You are going to use 2 quartz cuvettes, one for reference cell and another one for sample solution. Fill the reference cuvette 3/4 full with cyclohexane and the sample cell 3/4 full with a sample solution. Don't forget to pre-treat each cuvette before being filled. This picture illustrates how the optical components are aligned inside a spectrophotometer. The white beam represents the light path. Insert the reference cuvette into the upper cell holder and the sample cuvette into the lower cell holder. Make sure that the clear sides of cuvettes are aligned with the light path. A single reference cell can be used for the measurements of all 6 samples. For the spectroscopic measurements at 40 Celsius, all sample flasks should be kept in the 40 Celsius water bath for the minimum of 5 minutes before measurements, and follow the same measurement procedure done for the 20 Celsius samples. The pyridine iodine complex absorbs light at 415 nanometers. On the contrary, free iodine absorbs light at 520 nanometers. A collection of generic spectra of solution A through F is going to be displayed in this plot of observance versus wavelength. Capital A at the vertical axis represents observance. The peak for free iodine will be positioned at 520 nanometers, and the peak for the pyridine iodine complex will be positioned at 415 nanometers. Since solution A does not contain pyridine, complex has not been formed in the solution. As a result, there will be a single intense peak at 520 nanometers that corresponds to free iodine. 1.00 milliliter of pyridine stock solution was added to solution B. This causes the growth of a new peak at 415 nanometers that corresponds to pyridine iodine complex. Take note that the observance of free iodine at 520 nanometers decreases, implying that less free iodine is present in the solution due to the formation of complex. As you move down the table, the quantity of pyridine increases gradually in the solution. As a result, the peak at 415 nanometers grows while the peak at 520 nanometers shrinks. Collect and save 2 spectral plots of solution A through F like the one above, one for 20 Celsius and another one for 40 Celsius. Châtlier equation allows us to determine the equilibrium constant of the reaction graphically, utilizing the information from the previous spectra. Epsilon C and epsilon I represent the molar absorptivity of complex and iodine. Capital Ci and capital Cp represent the molar concentrations of iodine and pyridine in each solution. Take note that the concentrations of iodine and pyridine in solutions A, B, C, D, E, and F are different from the concentrations in stock solutions. Capital A0 represents the absorbance of solution A, which contains only free iodine. Capital A represents the absorbance of solution B through F, which contain both free iodine and complex. This is the same generic spectra taken from the previous slide. For data analysis, we will use only free iodine peaks at 520 nanometers. Like I said just before, the absorbance of solution A at 520 nanometers is denoted by capital A0. The absorbance of solution B at 520 nanometers is denoted by capital A, implying the absorbance of free iodine of solution B, and the absorbance of solution C at 520 nanometers is also denoted by capital A, implying the absorbance of free iodine of solution C. Same procedure should be also applied to solutions D, E, and F. Now, check the Châtlier equation above again. It has a form of y equals mx plus n. Ci over a minus a0 corresponds to variable y. 1 over Cp corresponds to variable x. 1 over Keq times epsilon c minus epsilon I corresponds to slope m, and 1 over epsilon c minus epsilon I corresponds to y-intercept n. Make a table like this one and fill the blanks. Use a spreadsheet software and plot your data like this. Find the equation for the best fit line or trend line. The m and n are given as numerical values in the equation for the trend line. The y-intercept n is equal to 1 over epsilon c minus epsilon I. The slope m is equal to 1 over Keq times epsilon c minus epsilon I. Surprisingly, a part of slope, 1 over epsilon c minus epsilon I, is the y-intercept. So we can rewrite the slope like n over Keq. Re-express the equation with respect to Keq, which is Keq equals n over m. Since m and n are numerical values that can be found in the equation for the trend line, we can easily determine the Keq values. Utilizing two sets of spectral plots, determine two Keqs, one for 20 Celsius and another one for 40 Celsius. Once two Keq values are found, we can easily determine two delta G naught values, one delta H naught value, and two delta S naught values. You should include at least the following items in your lab report. Number 1. Include two sets of spectral plots, one for 20 Celsius and another one for 40 Celsius. Number 2. Include two plots of Ci over A minus A naught versus 1 over Cp, one for 20 Celsius and another one for 40 Celsius. Number 3. Include this table with blanks filled. Delta H naught is assumed to be constant at 20 to 40 Celsius. Number 4. Use the two Keq values and determine whether the reaction is exothermic or endothermic. Rationalize your determination using Le Châtlier's principle. Show how your determination is consistent with two delta G naught values and the delta H naught value of the reaction. Number 5. Use the two delta S naught values and state whether the temperature change would affect the degree of randomness of the reaction mixture.